right, then let's start our next topic. So this is topic 3. This will be the last topic that will be on the exam. So up through this will be on the first exam. And I think it's important to make this disclaimer. So this unit, if you have a physical note packet, you'll have noticed this, but it's hefty. And we're going to spend a fair amount of time here just because it's extremely important to have a good foundation with this for the rest of the stuff that we're going to talk about in thermodynamics. Yeah. Yeah. Oh, yeah. So that's a good question. So before each of the exams, I will give you a practice exam and we'll go over it in class. And then just as full disclosure, I tend to write the practice exam at the same time as the real exam. So it's like my same headspace. I've heard that they're reasonably similar to each other from students. So, other questions about exams or anything? Okay. Okay, so this topic is extremely important. I think some students, have a little bit of a hard time with it just because it's kind of a weird thing that you've maybe never done before, but it's really, once you get the hang of it, isn't too bad. It's all about practice, in my opinion. So we're going to go through kind of all the nuts and bolts in class as well as a few examples, but I would encourage you to, beyond like homework assignments, if you have the book or any thermo textbook, just do examples until you're like, I'm bored of myself and of this. And then that's how you know that you've got it. Okay. Okay. So in the previous unit, in topic 2, hopefully you remember that we studied the principle of conservation of energy. And we've also introduced the concept of internal energy. Which we give the symbol lowercase u. And in order to apply conservation of energy to a system, we need to know the properties of the system and how they're related to each other. Okay, so we kind of stated that we needed to know that in the last unit, but we didn't really talk about how we might go about finding what those properties actually are in an actual engineering system. So that's what this topic is going to be about. How do we find the properties of our material at different states? Okay, so the first thing that we have to know about or define is what a pure substance is. And so a pure substance is characterized by any substance that has a fixed chemical composition throughout the system. Okay, so some examples of pure substances would be water, carbon dioxide, oxygen, copper. Sometimes mixtures, if the mixture has the same chemical composition. So for example, if you had a mixture of liquid water and water vapor, anywhere you are in that mixture, your chemical formula would be H2O, so you're good. And a mixture such as air also is okay, as long as it's in gaseous form. All right, form. So essentially the argument that we're making here is that generally air has the same mass fraction of all the different species that are in it, and it's well mixed. So that mixture composition is the same throughout a gas, as long as you're a gas. That changes if your air is in 2 different states. So if you have gaseous air and then liquid air, this is not a pure substance anymore. And I think this one is a little conceptually challenging to understand why at first. The reason for that is because air is made up of a bunch of different chemical components, right? You have nitrogen, oxygen, helium, all those good things. They will turn to a liquid at different pressures and temperatures. So when that happens, if you have part of the air mixture that's turned to liquid, it won't have the same chemical composition as the gaseous version because things turn to liquid at different times. Does that make sense? So let me just write that down so it's for the record. So the components of air change from gas to liquid at different pressure and temperature. Therefore, the chemical composition of the liquid is not equal to the gas. Okay. Another more obvious example of a mixture that would not be a pure substance would be if you have a mixture of, for example, water and oil. All right, they are not miscible, so those two fluids will not mix with each other. So as you move through this domain, the chemical composition changes, so that's not a pure substance. Okay? Any questions on how we decide if something's a pure substance or not? No? Okay. We also are going to care quite a bit about phases. So what phase a substance is in, whether that's liquid or solid, liquid or vapor, or whether it's a mixture of two or more phases. And then we make a note that each phase is going to be characterized by a boundary surface. So if you think of, we're probably all the most familiar with water and its three states. So if you have a container that has liquid water with a cube of ice floating in it and then water vapor over top, you can imagine how there is a specific surface that separates solid from liquid, solid from gas, and gas from liquid. And I think that's all of the combinations, but there's a surface that you can define that separates all of the states. Okay. For real substances, such as water, refrigerant 134A, ammonia, and so on and so forth, which cannot be treated as ideal gases, the equation of state which is an equation that's going to connect pressure, specific volume, and temperature. This can be very complicated. So just to remind you, hopefully you remember from, I'm guessing, chemistry, for an ideal gas, and we'll talk about this in more detail later in class, but for an ideal gas, the equation of state is PV equals nRT or similar, right? There's a few flavors of that equation, but that's the ideal gas law. So that connects pressure, volume, and temperature, right? So for other substances that are not ideal gases, we don't have the benefit of being able to write down a nice equation like this. And instead, what actually happens is something that looks like this. So this is a graphical representation of what the equation of state looks like. For on the left, we have a substance. So on this left picture, we have a substance that contracts on freezing. So if it freezes, it gets occupies a smaller volume. And then on the right-hand side figure, this is a substance that expands upon freezing, so it gets bigger, like water does. Okay, so you'll notice on here that we have three axes. So equation of state is always going to relate pressure, volume, and temperature. So we have pressure on our vertical axis, volume on the first horizontal axis, and then temperature on the third. So we have volume, pressure, and temperature. All right, so we end up with a surface relating all of these things. So you'll notice that there is a region on this where we have our different states of matter. So for example, we have the gas phase is in here. Our solid phase is over here. And then our liquid phase is here. And there are a few sharp points in here where we have critical points that exist. But this is kind of hard to deal with, right? So if you wanted to look up a property based on pressure or volume or temperature, using a chart like this is going to be very difficult to figure out what the value would be, obviously. So instead, it's more common to have thermodynamic properties given in tabular form. Okay. So to talk about kind of these different state changes and kind of how we traverse the different states and some terminology, we're going to do an example or kind of talk about a piston cylinder of water with heat being applied to it as an example. So we have liquid water that's being heated, and we start at 1 atmosphere of pressure and we keep it at 1 atmosphere of pressure for all 5 of these states, and we're applying heat. So we start off with liquid water, and we're given that it's at 1 atmosphere of pressure and 20 degrees Celsius. The temperature is then going to go up between state 1 and state 2. So when we get to state 2, we still have our 1 atmosphere of pressure, but now our temperature is up to 100 degrees C. And this is water. Can anybody tell me what might be happening here? Has the volume changed? Do you think? Yeah, so this is the boiling point of water. So we're right at the cusp of boiling here. So this volume is going to be very slightly larger than the volume when it was at 20 degrees C. And so, and actually let me go back here. So state 1, we call this a compressed liquid. All right, so the water is a liquid phase. It's called a compressed liquid. Or a subcooled liquid. I would say that compressed liquid is much more commonly used than subcooled liquid, but they both exist. And what we mean when we say that is that it's in liquid form, but it is not close to vaporizing. So it's not close to its boiling point. Okay. At state 2, we have a liquid that is very close to becoming vapor. So it's at its boiling point. So the term that we give this state is a saturated liquid. All right, so a phase change process from liquid to vapor is about to take place. And so this means that the liquid is saturated. Saturated. And when we talk about properties at the state, we are going to give them a subscript F. So you can think of this F as indicating fluid about to become vapor. All right. So we will use things like the specific volume of that saturated liquid is VF, the internal energy is UF, enthalpy is HF, and then entropy is SF. So this is entropy. We'll talk about this in chapter 8. So not in this unit in particular are we going to really talk about entropy. And then as a reminder, we talked about this in the last unit, but enthalpy is related to the internal energy plus, oh, sorry, not the subscript F. Sorry. So in general, enthalpy is related to the internal energy plus pressure times specific volume. So that is always true, whether you're at a saturated state or not. Okay. And here it's also worth noting that terminology wise, if at a given pressure, the temperature at which a pure substance will start to boil or condense, if you're going in the other direction, is called the saturation pressure. Or PSAT. PSAT. So for example, oh gosh, I'm sorry. We're talking about temperature right now. So this is saturation temperature or TSAT, and I spoiled it myself, but we're going to talk about saturation pressure as well in just a second. But for example, water at a pressure of 1 atmosphere, the saturation temperature, does anybody know what it is? So what's the temperature that water will either boil or condense at standard pressure? Not a trick. Oh yes, 212 Fahrenheit or 100 C, right? So this is just what we're kind of used to thinking of as a boiling point, right? We're going to call it saturation temperature. Water at 1 megapascal, which is 1,000 kPa, has a saturation temperature of 179.9 degrees C. Okay, so the key takeaway here is that saturation temperature is a function of both whatever the substance is. So it matters what substance you have. Everything will have a different boiling point, obviously, or a saturation temperature. It's also a function of the pressure. All right, so you can see that for water here, our saturation temperature goes up quite a bit when we increase our pressure. Okay, so that happens for all substances. Any questions on that so far? Okay. So I already kind of started doing this on accident, but just like how we have a saturation temperature, we also have a saturation pressure. So our saturation pressure, or PSAT, is the pressure at which a pure substance starts to boil or condense. So for example, water at 100 degrees C has a saturation pressure of 101.3 kPa or 1 atmosphere, right? And then we can work the other way around. So our water at 179.9 degrees C has a saturation pressure of 1 megapascal. Okay, so our saturation pressures and temperatures are connected with one another. Does that make sense? Cool. Okay, let's go back to our little example where we're heating. So we're gonna keep heating this fluid, this water. And you'll notice that from state one to, or sorry, from state 2 to state 3, our temperature is staying the same. All right, but instead of having our saturated liquid, we're now looking at a liquid vapor mixture. So here we have a saturated liquid vapor mixture. Okay. Then going from state 3 to state 4, we still keep our temperature and pressure the same. So this is still a constant temperature. But now we have that all of our water is a vapor. So we call this state a saturated vapor. Okay. And so all of these, so states 2, 3, and 4 are changing state, right? We're going from a saturated liquid. Parts of that saturated liquid have transitioned to vapor, and then finally it all becomes vapor. But the pressure and the temperature is the same for all these configurations because we're having our state change due to changes in internal energy. Okay. So at state 3, oh, what color did I give that? Teal. The water consists of a mixture of saturated liquid and vapor, and is referred to as a saturated liquid vapor mixture. And then at state 4, we're still at the same saturation temperature. And when this happens, any heat loss, even if it's very, very small, it will cause some of the vapor to condense. And so in other words, a phase change process from gas to liquid is about to take place. A vapor which is about to condense is called a saturated vapor. And we designate these properties with a subscript G. So before we were using subscript F, like fluid, G, like gas, okay? So just like how we had before, we have the specific volume of a saturated vapor, the internal energy, the enthalpy, and the entropy. Okay. Thermodynamic properties at saturated liquid and saturated vapor states are tabulated either as a function of temperature or as a function of pressure. So just like how we kind of had 2 ways of looking at the saturation temperature and the saturation pressure, that's how the tables are going to look. So we're going to be looking at these tables a whole bunch. So I just kind of wanted to walk through everything that's going on here quickly, and we'll do this more than once. You'll probably get tired of me talking about it, but that's okay. So this top table here, and these are in the textbook, if you have the textbook, and I also have these tables reproduced on Moodle as well. But table A4 is going to give us the temperature table for saturated water. So we have this is saturated water. Both of them are for water. Obviously, these tables exist for other substances as well. And then our top table here, this is a temperature table. Okay. And then the second table below it is a pressure table. All right. So you'll notice that the way it's organized is a little bit different. And essentially what we have is that in the temperature table, we have a column for the temperature, and then we can find out what the saturated pressure is. Whereas for the pressure table, it's the opposite. So we're given the pressure, and then we can find out what the saturation temperature is. All right, and those are in these columns here and here. Okay, and then you'll notice that we have essentially 4 big headings that exist here. So we have one for specific volume. So this is our V. And then under that heading, there's 2 options. So if we are in the saturated liquid phase, we would be looking for specific volume for a saturated liquid, which is VF. And then if it's a saturated vapor, we'd be looking at this column. Okay. Same thing for internal energy. So this is U, enthalpy is H, and then entropy is S. And all these symbols are given in this row as well. But this table is nice because it gives you the written out name, the units, and the symbol. Okay. And then we have the same sort of thing for our pressure table. So all of the information kind of in the bulk of the right-hand side is structured in the exact same way. We're just inverting that we have pressure and saturation temperature rather than temperature and saturated pressure. Okay. We'll do practice using this, but I just wanted to show you kind of how they're structured. Okay. Oh, another note. So in the book, the tables that end with the letter E, that means English units. Okay, if it doesn't have an E at the end, that means it's SI. So always check the units in the table that you're using and make sure it's consistent with the problem you're doing. Okay. Okay, so if we continued heating our container of water beyond state 4, the water is going to stay a vapor, and then the temperature begins to increase beyond the saturation temperature. All right, so we're just heating up that substance, but it's not changing state anymore. And when that happens, we call that a superheated vapor phase. Meaning that it's not about to condense. So we have a vapor that's not close to condensation. It's a very hot vapor. All right. So if we go back to here, so we are going to continue heating. So we have that T4 is less than T5. And then this is our super heated vapor. Okay. And that's the terminology for going from a liquid and then heating it up through to a vapor at constant pressure. Okay. It's helpful to look at this on a curve or on a plot, which is called a PV diagram. So I'm going to put temperature on this axis, and then I have specific volume, which is of course the total volume divided by mass on this axis. All right, so if you recall, we started this at 20, and this is T in degrees C. So we started at 20 degrees C, right? And this was state one. And then we ended up heating up our fluid to 100 degrees C, and its volume, its specific volume increased a little bit. So just slightly to get to state two. And we said that once it was at state two, this is what we call a saturated liquid. So this is VF, right? And then our temperature stayed the same while our specific volume increased. And this happened a couple of times. So we went from 2 to 3, and this is our saturated liquid vapor mixture. And then at state 4, which is our saturated vapor, which has specific volume VG. So this is our saturated vapor. Then as we continue to heat it here, we go up on a curve like this to get to state 5, which is a superheated vapor. And then I should put down here, so this part of our curve is a compressed liquid. And then the tail end on the high specific volume, high temperature side is our superheated vapor. Okay. So essentially just walking through what that container of water did was we had it cold, not close to boiling. So it was a compressed liquid in that state. As it heated up, we got to the saturation temperature for that pressure, at which point it became a saturated liquid. So it was just about to turn into a vapor. And then as heat was added to it, but the temperature remained the same, we start to see the state change, and it goes from saturated liquid to a mixture of saturated liquid and vapor, all the way to a fully saturated vapor state. And then beyond that, if we continue heating it, we get a superheated vapor. Does that make sense? Okay. Does anybody know what is special about this line that I've drawn? What was held constant throughout the entire process? Does anybody remember? Temperature changed, right? Specific volume changed. Pressure stayed constant, right? So this is an isobar, or constant pressure. Here. So oftentimes what's done is at the end of this line, we will have P equals 1 atmosphere. So we'll say, what is the pressure for this isobar curve? And as you can imagine, for every pressure that we could apply to our little system of water, we'll have a different curve. Okay? Okay. The other thing that is worth noting here is that if we did this entire process in reverse, the curve stays the same. We will follow the same path. We will just be moving from state 5 to state 1. Okay, but everything else stays the same. All the names are the same, all that stuff, process is the same. So We repeat this entire process in reverse. The process will follow the same or isobar. Okay. Okay. Another quantity that we are going to make use of is called the mixture quality. So, for example, if I include another point on this curve above called 3 prime, so I'm going to put 3 prime here. All right. So both of these are at a temperature of 100 degrees C and pressure of 1 atmosphere, and they're both in the saturated liquid vapor mixture phase, right? So we'd like to distinguish between those two in some way. And so what we do is we use the mixture quality. So my question to you is, are these at the same state? Is our substance at 3 prime and 3 the same state? Any ideas? I see a nodding yes. So it is, but with a caveat. So both states are in the saturated liquid vapor mixture kind of category, but they're not exactly the same state um, because the volume of saturated liquid compared to the volume of saturated vapor is different from 3 prime to 3. Okay, so the composition of those two different states that are in the mixture changes. So the reason is they have different volumes and therefore specific volumes. And the proportions of liquid and vapor in each mixture are different. You also might remember that when we talked about what is a state of a substance before, I think in the first unit, we talked about all the qualities have to be identical, right? So the specific volume, the pressure, the temperature, all of those things have to be identical, but the specific volume is different from 3 prime to 3. Yes. Yeah. Oh, it is a liquid to a gas. Sorry, I misspoke if I said that. Thank you for clarifying though. So for just to reiterate, so in this example, we're going from liquid to a vapor. You can go in the other direction from a vapor to a liquid, right? So it doesn't matter which direction you're approaching it. It's a saturated vapor if you're either a vapor about to become a liquid or a liquid about to become a vapor. And then the same thing for a saturated liquid, whether you're a vapor about to come, or whether you're a saturated liquid vapor mixture about to become liquid or a compressed liquid about to become a saturated liquid vapor mixture, it's still called a saturated liquid. Does that make sense? So we can look at it in either way. Okay. Okay. So in order to differentiate between two different saturated liquid vapor mixture states at a given pressure or temperature, what we're going to define is a property that we call the quality. And it's going to be assigned the symbol X. Okay, so comparing state 3 prime with state 3, what can we say about the amount of vapor in state 3 prime versus 3? Yeah, there's less. Very good. And so that means that the quality of the mixture we can define as X is equal to the mass of vapor divided by the mass of the mixture. So this is mass of the mixture, or you can think of it as the total mass. And then obviously this is the mass of the vapor in the mixture. All right, and this has no units. Because we're taking the units of mass divided by units of mass, so we have no units. And we can also use this to say that the total mass of the mixture is mass of the liquid plus mass of the vapor. That's just conservation of mass, right? Using quality is only valid for saturated liquid vapor mixtures. Okay, so we're only going to use this when we have a mixture of those two states, including the saturated liquid and then the saturated vapor points. So it will exist, if you recall our TV diagram. So we had something like this, right? This was our diagram. So X is only valid in this region. Okay, including these 2 points. Okay, so it has no meaning in a compressed liquid or a superheated vapor region because it's not a mixture of things, right? Both of those states are all vapor and all liquid, so the idea of equality doesn't make any sense, okay? But let's talk about kind of the bookend values for quality. So given that quality is defined as the mass of vapor over the total mass of the substance, what do you think X would be for a saturated liquid? How much mass of vapor do we have for a saturated liquid? 0, right? Yeah, great. So that means that X is equal to 0. And then for a saturated vapor, how much mass is vapor? Yeah, it's M, it's all of it, right? So then we have that X is equal to 1. So that means that for a mixture of liquid and vapor, our quality is going to be bounded by 0 and 1. The closer it is to 0, the closer it is to mostly saturated liquid, and the closer to 1 it is, the more it's mostly saturated vapor. Does that make sense? Okay. That being said, if you end up with a value that's less than 0 or a value that's greater than 1, you have made a mistake somewhere. So check your work. Or the phase is perhaps not a mixture, so just be careful. All right, so you'll always get something between 0 and 1, inclusive of 0 and 1. Okay, so let's talk a bit more about saturation temperature and saturation pressure. So one thing that's really important to note is that these two quantities are dependent properties for a given pure substance. All right, so that means that there exists a definite relationship So essentially, Tsat is equal to some function of Psat and the other way around. And saturation pressure is equal to some function of saturation temperature for every substance that exists. Okay. The temperature at which a substance starts to boil depends on the temperature or the pressure, sorry. And therefore, if the pressure is fixed, so is the boiling temperature and vice versa, right? So if you have a substance at a certain pressure, the temperature, oh no, I did that backwards. So vice versa. So if you know the temperature, then the pressure at which it boils is going to be fixed, if that makes sense. Does that make sense? Okay. Um, so we can make a plot of the saturation pressure versus the saturation temperature, and that is called a liquid vapor saturation curve. Curve. And for reference, if you are following along in the textbook, tables A4 and AE, so this is the same table, but just in English units, are going to show Tsat as a function of pressure for water. And then, oh, I did this backwards. Sorry. That's table A5. No. Okay, and then 4 shows Psat as a function of temperature for water. Okay. So an example of what one of these liquid vapor saturation curves looks like is the one I've shown right here. So this is for water. You'd have a different curve for a different substance. And then we can also use the idea of elevation changes changing pressure to connect Psat, Tsat to an elevation on Earth. So this is just since pressure changes with elevation. All right. I don't know if any of you cook, but if you are someone who cooks, you might have noticed that recipe instructions will be slightly different if you're at altitude. And this is why. So when you're at altitude, the saturation temperature of water is slightly different because the pressure is different at altitude. Okay. You probably didn't think you were going to learn about cooking today, did you? All right. Okay, so suppose that we did our exact same piston cylinder experiment. So the one where we had water that started at 20 degrees C and we applied heat to it and we kind of brought it through all of those different states from condensed liquid all the way up to a superheated vapor. We could repeat that same experiment for a bunch of different pressures, right? And for each different pressure, we're going to get a different curve for how it goes through the different states, right? So what we see happen here is that these points right here is where it becomes a saturated liquid. So this is Tsat. All right. And then this is the point at which it becomes a saturated vapor, right? So what's often done is that we can connect all of these points with a curve. This is much harder than it looks. Okay. like this. No, that's annoying. All right, so we have our curve like so. All right, and each of these lines here are our different experiments for different pressures. So each line represents an isobar. These are constant pressure lines. Okay, and you'll notice that there is kind of a shift of how these curves look from a very kind of specific angular point where we're going from a condensed liquid to a saturated liquid, and then from a saturated vapor liquid mixture to a saturated vapor. So that starts to smooth out once we get to really high pressures, right? So these curves up here, they start taking on a very distinct kind of smoothed out shape, right? Um, so once we lose that kind of definitive point where we're switching from saturated liquid to vapor, which is right here, this is what we call the critical point. Which, yeah, okay. So at, for water, so at P critical, which is 22.06 megapascals for water, the saturation line will become a point and the temperature is T critical, which is 373.95 degrees C. Again, this is for water. And this point is called the critical point. And it's defined as the point at which the saturated liquid and saturated vapor states are identical. So we skip that mixture region of transitioning from a saturated liquid to a vapor, and it goes immediately from saturated liquid to saturated vapor. Okay. I forgot to put on here, this black line is called the saturation line. Sorry. All right, so if you think about it, everything underneath the bell of this curve, so everything in here represents a saturated liquid vapor mixture. Everything over here on the other side of this curve is our compressed liquid. And then I need another color. And then everything over here is our superheated vapor. So this is superheated vapor. Okay, so does that make sense? This line is representing kind of our change from compressed liquid to superheated vapor, and then everything underneath that curve is a mixture of those two things. Good? Okay. Okay. At pressures that are above the critical point, there's no distinct phase change process. So instead what happens is our specific volume is going to continue to increase, and at all times there will only be one phase present. So it's either one or the other. There's none of this mixture business going on. Okay. Eventually, it will resemble a vapor, but one cannot tell when the change occurred. All right. Beyond the critical point, liquid and vapor phases cannot coexist. In equilibrium. And then, oh, this is just a reference. So everything that I'm showing you, all the tables I'm showing you in these notes are the tables for water. Appendix A1 and A1E, depending on what units you want, list critical temperatures and pressure values for substances that are not water for reference. Any questions on this so far? Okay. Okay. So we looked at the TV diagram before when we were talking about our kind of water heating and state change experiment. So we're going to talk about TV diagrams a little bit more. In particular, the saturated liquid states in the figure that I showed you before can be connected by a line called the saturated liquid line. And the saturated vapor states in the same figure can be connected by another line called the saturated vapor line. All right, so what I call the saturation line, we can divide it in halves, and one half is the saturated liquid line, the other side is the saturated vapor line. And they meet at the critical point and form what is known as the vapor dome. All right, so essentially what we have, did I include, oh, okay, never mind, it's here. I was gonna draw it for you, never mind. So we have our saturated liquid line. Oh, let's call that orange. So our saturated liquid line is just this side of the saturation line. So it's the left-hand side of the line up until the critical point. And then our saturated vapor line is just the other side of it. All right. And then this whole thing is the vapor dome. And if you're in the vapor dome, then you're a mixture of saturated liquid and vapor. Okay. Again, just to reiterate, these are all constant pressure. And then as you go up, this is increasing pressure. All right, so these curves increases in pressure as you go up the dome. All right, another thing that's worthwhile to look at here is each of these intersection points, if we trace down, are going to give us our VF of state one. So if this is my configuration one, for example, so I'll call this, sorry, I'm going to call this pressure one curve. This other one's called pressure one. I'll call this pressure zero. So this is VF zero. And then this is VG zero. Okay, and then we can do that for each of the pressure curves going up. So this is then our specific volume F of pressure one. And then we also have VG1 and so on and so forth. So we can keep doing this for any pressure that we want. Okay. And then similarly, we can look at the saturation temperature at the various pressures. So if we're looking at our pressure curve 0, then this temperature is our saturation temperature at P0. This is our saturation temperature at P1. And then this is our saturation temperature at P2. Does that make sense? And then if we look at the temperature where this critical point happens, this is T crit, critical temperature. Okay. Any questions on this so far? Okay. Okay, so you guys still have this space here, right? Okay. I want to add a couple of notes here. So the TV diagram was developed using constant pressure processes, obviously. So those lines that show up are we're doing the state change over a constant pressure. So that's how we're making all of these curves. So it's developed using a constant pressure process. But it's actually a unique representation of the phase state of a pure substance. So what this curve looks like will change depending on the substance. All right. Do I? Okay, sorry, just wanted to double check. Let's also, I wrote this down earlier, but I'm going to formally define it here. So specific enthalpy is just a combination of internal energy, specific internal energies, pressure, and specific volume. So this is internal energy. Specific volume, and then this is pressure, of course. All right. So we can make a bunch of other similar diagrams to the TV diagram using the other properties that we care about for pure substances. So we can also make a TU diagram, a TH diagram, or a TS diagram. And these are similar to TV diagrams. We can also make a PV diagram. So the most popular diagrams that you'll see are TV and PV diagrams, but you can construct all of them, right? So for temperature, internal energy, enthalpy, entropy, and pressure, you can make these curves, okay? And just to show you what a PV diagram looks like, it's very similar to a TV diagram. So we have now, instead of lines of constant pressure, we'll have lines of constant temperature. And they will look something like this. So this is T1. where we have our critical point or our saturation points here. And then eventually we'll also reach a high enough temperature that we reach this critical point where there's no vapor liquid mixture region happening anymore. All right, and so our vapor dome now looks like this, which is very similar, but you'll notice that we have, instead of the constant pressure curves here, we have constant temperature curves. And this is structured in the exact same way. So this is another version of a vapor dome. We have a saturation line that's divided into compressed liquid and vapor, just like how we had for the TV diagram. Does that make sense? Okay. Okay. So let's talk about some rules. If we refer to a TV or a PV diagram and we want to determine the phase of a substance, let's consider some specific cases. So if we're given a temperature or a pressure and the specific volume, and our saturated liquid, so our specific volume for a saturated liquid, and then this should be G, sorry. So this is saturated vapor. So we have found that the calculated specific volume, this is what we've calculated, it lies between VF and VG. What state would that be? Where are we on a TV diagram? Yeah, we're under the dome. So that means that we have a saturated liquid vapor mixture, right? Does that make sense for everybody? So this is a saturated liquid vapor mixture. Okay, so that would be, for example, if I'm going to just try to use the same colors here. Ah, darn. So for example, if we have, this is our VG, and then this is our VF, and then our specific volume that we've calculated is somewhere in here, then that means that we're in the saturated liquid vapor region. Okay, does that make sense how we're kind of using this chart to decide that? Okay, cool. What about if our specific volume is greater than VG? Ooh. Sorry, say again? Yeah, so this is a superheated vapor. So I will call this the red. Oh my goodness. So now we have this specific volume is greater. So we're here. All right, so this is a superheated vapor. Fantastic. And then what if our specific volume is less than or equal to VF? Compressed liquid. Fantastic. So that would be if we are over here, for example. Okay, so this is compressed liquid. What if V is equal to VF? Yeah, saturated liquid. And then what if V is equal to VG? Yeah, saturated vapor. So we're just, those are the definitions for what a saturated liquid and a saturated vapor are, right? Okay, fantastic. Let's extend this diagram, our PV diagram, to include the solid phase. All right. So the liquid vapor phase diagrams that we looked at so far included compressed liquid up to a vapor, but they didn't have the solid in there, right? So we can also include the solid liquid and then the solid vapor saturation curves, right? So we can go from liquid to solid, solid to liquid, and then sublimation is when solids go to vapor. Okay, so for a substance that contracts on freezing, here's what that looks like. So we have specific volume against pressure for both of these. All right, and so we'll have our same vapor dome as we had before. So this is the same vapor dome as before on both of these. But now we will have a couple of changes. So this is what's called the triple line. So under our dome, we still have liquid and vapor. Liquid and vapor. And then under this triple line, we have solid and vapor. All right. And this triple line extends a bit further for a substance that contracts on freezing. And then we have a line here where we have solid on the left-hand side of it. And then we also have a line here that is, this region is solid and liquid, like a slushy. And then over here, we have just compressed liquid. And then of course we have vapor over here, just as always, with our critical point. Okay. If our substance expands on freezing, we no longer have our solid line is a little bit different. Right, so this is our solid and liquid. Here's our solid. And then of course liquid and vapor is the same as the other side. Okay, so here's what this looks like when we include the solid as well. In this class, we're going to primarily concern ourselves with the, liquid to vapor continuum of states, but this is the solid kind of in the mix as well. Okay. Most substances contract on freezing. Some substances expand. So water, of course, is one of them. And then also silicone, gallium, and antimony and bismuth also expand on freezing. That's interesting. Tuck that away for trivia. Yes.
That little triangle there.
It's a good question.
Okay.
So this is, I should have drawn this as, oh geez. I should have drawn this as like dashed inside of here. Because this isn't really the vapor dome anymore. So that should be still solid and liquid in there. Okay. Okay. Um, we can also, so this is a PV diagram. We can also do a PT diagram, which is known as a phase diagram. This is probably what you're more used to seeing when talking about state changes, I'm guessing. And this one shows expanding and contracting substances on the same plot. So substances that expand on freezing are shown with this dashed line, and then the ones that contract when they freeze are this line. Okay. One small note here, this vaporization line, you can also think of it as a condensation line, because vaporization and condensation are the same things, just in opposite directions. And then yeah, okay. Let's see. At the triple points, which I mentioned on a couple of these plots, but didn't really talk about too much. The triple point means that all three phases exist in equilibrium. So you have liquid, vapor, and solid existing. So that is here. Couple notes about this. So points that fall on a line are in a mixture involving the two phases that separate the lines. P and T, so pressure and temperature, are independent in a single phase region, but they are dependent in a two-phase region. So if you set PSAT, then TSAT is fixed, and then vice versa. Okay? All right, cool. Okay, so let's talk about some more rules for phases. So if you are given a temperature, you can look up the saturation pressure at that temperature in the saturated temperature table. And conversely, if you're given pressure, you can look up the saturation temperature given that pressure in a saturated pressure table. Okay, so they're just different tables for doing those things. If you are given temperature and pressure, if the pressure is less than the saturated pressure for that temperature, and I'm going to draw a sketch really quick so that we can answer this question a little more easily, but you can scroll back and forth if you want. So let's say that this is our phase diagram. So this is liquid. This is vapor. And this is solid. Okay. All right, so if if we are given T and P is less than the pressure of saturation at that temperature. So we are looking at so for example, if we're given T, make this dashed. So if this is T that we're given, that means that this intersection point, this is P sat at T. All right, so if our pressure is less than P sat, what does that mean about our state?
the vapor.
Yeah, so it's I'll do one even better. It's a superheated vapor. Our saturated vapor would just be on the line. Okay. Okay, what if pressure is greater than our saturation pressure? Pick a color. We're going to increase our pressure. So now we're going to compress liquid, right? Okay, what if we're given a temperature and a pressure, and the temperature is less than the saturation temperature at that pressure? Actually, let me go back to the other one because I want to make a comment. So for the one with the red dot, so we said for a given temperature and pressure, if P is greater than the saturation temperature, it would be a liquid. It could also be a solid, technically, right? Okay. Um, now we're going to have a look at a pressure. So let's say that we have some pressure, and I'm going to draw, this is getting busy. I'm sorry, guys. So this is our pressure line. All right, and our temperature is less than the saturation temperature. So our saturation temperature, there's two choices for this. So our saturation temperature, depending on where we're currently at, could be here or here, right? So depending on where we start off, if our temperature is lower than that, then we're either a liquid or we're a solid, depending on what state we started at. Does that make sense? So this is compressed liquid or a solid. All right, and then conversely, if the temperature is greater than the saturation temperature at a given pressure, so if our saturation temperature implies that we're at the solid liquid boundary, then that would mean that we've moved into a liquid, and then if we're at the liquid vapor boundary, then it could be a vapor. Okay. And then finally, if our temperature is at the saturation temperature or our pressure is at the saturation pressure, then that means that we are a saturated liquid vapor mixture. Because if we're on the line, then that means we're a mixture. Okay. Okay. So, if we are in this category, this means that in this case, P and T are not independent. So we need to know the quality like the quality, or we could know the internal energy, specific volume, H, or entropy to define the state. Okay. Okay, this is a fairly good stopping point for the